rates for mobility. So some of this, we've just gone over. We only have, 19 or 18 minutes or so. So we won't get through all problems today. I'll pick this back up on Monday. But this is really intended to be an application sort of lecture to just work some examples and sort of, cement in the process for solving the differential equation problem. I'll try and fix this in the notes. These are lecture 7 notes. They're posted online as lecture 7 notes, but I forgot to change the material. Okay. So, again, you'll be able to write this equation in your sleep by the time we finish chapter 3. We talked about how this equation is derived from conservation of momentum setup due to the second law. But you can think about the Rayleigh equation, and you can also arrive to the same equation by thinking or deriving from the concept of conservation of energy. So what we've sort of discussed or created here is an expression that says that we have 3 forms of energy along the streamline: the energy embodied in the static pressure, the energy embodied in the moving fluid, and the energy embodied in relation. Those 3 things sum to a constant. So if we look along points that are connected by a streamline, at any given point we can write these 3 things, sum them up, and say it's got all equal. Okay? So some problems that you'll be presented, you'll have to extract from the word problem, or otherwise, or maybe interpolate on a table or something. You'll get 5 or 6 variables and solve. Right? That's one way that you'll be asked to use the Bernoulli equation. A lot of other scenarios involve invoking conservation of mass to reduce the amount of unknowns that we have. Okay, and this becomes convenient and simple because we have incompressible flow, and so as flow moves through changing geometries, right, the thing that can change with that is only the velocity. Right? So this is, I think, a simple concept, but it's easy to get sort of tripped up on what we're talking about when we say conservation of mass. So I want to work through a quick example that I hope makes this clear, and then just provides some quick practice on calculating these flow rates using cross-sectional areas, or calculating velocities using cross-sectional areas. Okay, so sort of to drive this point home, I have a relatively simple problem that we'll work through on volumetric and mass flow rates, and the use of a very simple version of the continuity equation. So the problem says a garden hose is used to fill a water bucket. The garden hose has a diameter of 1 inch, and the velocity of water leaving is 8 feet per second. Okay? So the first problem says to calculate the mass, or the volumetric and mass flow rates. Okay? We want to know the time to fill a 20-gallon bucket, and we want to know the average discharge at the velocity and the hose if you change the diameter of the hose. If it gets changed from 1 inch to 0.5 inches. Okay? So, just in the interest of time, this is definitely one set of problems to practice. I think if you work through this once or twice, you'll nail it down, but there are key concepts that allow you to advance on certain Bernoulli problems. Okay, so let's calculate the volumetric flow rate. How can we calculate the volumetric flow rate leaving that hose, given the information that we have? Yeah, right. So straightforward, right? Q, again, I'll use Q to describe flow rate, is equal to area times velocity, and hopefully you can all see that dimensionally, right? We have length squared for area, we have length per time for velocity, so dimensionally that gives us the volumetric flow rate of length cubed per time. And so we have an area of, or a diameter, we're given a diameter, so area is pi times the diameter squared over 4, or pi r squared. I know this is sort of tedious, but these are mistakes that I often see, right? So we want to do pi r squared, right? Make sure you drop that 0.5 in, right? Pi r squared is the area. gallons, you're told the velocity is 8 feet per second. Right? So I just inserted the conversion from inches to feet into the area calculation, so you should get 0.044 cubic feet per second. Okay, so how do I calculate a mass flow rate from that? So I'll use m dot to denote mass flow rate.
Multiply by the density?
Yeah. The mass flow rate is simply the density times the flow rate, right? Okay, simple stuff, but again, let's just work through a quick problem and make sure we're all on the same page about it. So, what's the density of water in English or US units? 1.9 slugs per cubic foot, something like that. Let's get that slugs unit in there. Times 0.044 cubic feet per second, right? Cubic feet cancels, we get slugs per second. This is a number, I don't have it written down. Okay, I'll do that. Equals a number. Okay, what about the time to fill the bucket? How do I calculate that?
The volume of the bucket divided by the volumetric flow rate?
Yeah, exactly. Yeah. And so if you ever sort of want an exam, just you don't want to write these down or you forgot to write them down. I mean, this is basic dimensional analysis stuff, right? So the dimensions of this, we have a volumetric unit divided by the volumetric unit per time. The dimensional analysis works out to time, right? If you sort of think about this, it makes sense, right? You have a flow rate, you have a volume, you can combine those things to get to the amount of time that it takes. Okay, so that gives us time. So we have a 20-gallon bucket. We have a flow rate of 0.044 cubic feet per second. We need to convert from gallons to cubic feet. So in 1 cubic foot, there's something like 7.5 gallons, 7.4 gallons, I think, 7.48. And so that should be 613 seconds. Okay, easy stuff, but again, easy to get hooked up on or sort of forget the dimensional analysis here. Okay, so the next part, this is sort of our invocation of conservation of mass, or the continuity equation that we'll use in this class, often in the Millie problems, is we essentially have a scenario where we're changing that diameter, right? You can think of it as like we're going from a 1 inch down to a 1/2 inch hose, right? I mean, we're not, maybe we've added an attachment to make that change, or maybe we swapped out the hose, but conceptually it's what's happening, right? We have flow moving through a higher area region, and then it necks down to smaller area region. Okay, but the key assumption, right, is that the mass flow rate at 1 has to equal the mass flow rate at 2, right? And we know how to calculate the mass flow rate, right? So the mass flow rate at 1 is the density of the fluid times the flow rate at 1 is equal to the density of the fluid times the flow rate at 2. What can we say about Q1 and Q2? They have to be equal, right? Because, I didn't add a substrate because I'm sort of jumping ahead and stating that the pressure is going to be constant, right? So that pressure has to cancel out. I'm sorry, density, yeah. That density has to cancel out, right? And Q1 has to equal Q2, okay? So our expression of the continuity equation that we'll utilize frequently in this class gets back up to what we've expressed here in part A. we'll use this frequently and say that the cross-sectional area at 1 times the velocity at 1 is equal to the cross-sectional area at 2 times the velocity at 2. And that allows us to express the velocity at a different location in the fluid flow and put it in terms of velocity somewhere else. It allows us to reduce variables in our Bernoulli equation derivation. Okay. So to sort of see this through, we know that A1, B1 has to have units of, or has to, A1, B1 has to be equal to this, right? We've already calculated it. So we have 0.044 cubic feet per second. Equals the area of 2 times the velocity at 2. Okay, so we solve for V2, 0.044 cubic feet per second. Again, being careful that we do pi r squared, sort of combining a variety of conversion factors all into one step, right? Yeah. Okay, so that, I think I might have a math mistake here. I think that should be 3.2 feet per second. Actually, I think that's equal to a number, right? It's a number bigger than 0.044 feet per second. It should be bigger by a factor of 4. So, I think I got the math. Hopefully. Okay, makes sense? The key here is that this is the equation that you invoke frequently, right? Our flow rate is not going to change throughout our fluid flow, and therefore we can break that down into a cross-sectional area of the fluid flow times the velocity moving through that cross-sectional area in one location is equal to that same expression, the cross-sectional area at a second point times the velocity through that second cross-sectional area. Okay? Okay. So this example asks to develop an equation for what we call a confined flow. These are the types of examples where you'll be asked to invoke continuity. So if you see flow moving through, constrictions that are in flowing pipes, where the diameters of the pipe are changing, those should all be clues that you're going to need to invoke continuity with your Bernoulli equation to be able to simplify the amount of unknowns that you have in the Bernoulli equation application. Okay, so the task here should be to develop an equation for the change in pressure, delta P from 1 to 2. And so this visualization is intended to, this is taken from an older version of the text, but this is intended to give you sort of a visual representation of what we're talking about when we talk about this simple application of continuity equation. Right? So we have a constriction here, we have some velocity, uniform velocity here, V1. So in some amount of time, this is the amount of volume that gets moved through the tube here at point 1. In that same amount of time, the same amount of volume has to get moved through point 2, but it has to do so at a higher velocity to achieve that same amount of volume. So maybe that visual helps you sort of see that, the sort of changing the shape of that parcel as it moves through different geometries of the tube. Okay, let's go ahead and work up our Bernoulli equation, and let's do it from point 1 to point 2. In this application, I can sort of draw my streamline straight through those two. There's no sort of impedance of the streamline upstream or downstream of that. So I've connected points 1 and 2 along a z datum where z equals 0. And I'm going to assume my positive z direction is upwards. Okay. This will look familiar to some of the problems we've worked out already. 1/2 rho v1 squared plus again z1 is equal to p2 plus 1/2 rho v2 squared plus again g2. Okay, so what can I simplify here? This is similar to a problem we've done already. We have pressure at point 1. Yeah, we have velocity. Z1 we put on our datum. So Z1 and Z2 go away. And then similar, we have pressure and we have velocity at the second point. Okay, so we can cancel out the Z's. We're asked to solve for a pressure drop, del P. So let's solve for P1 minus P2. And that'll be equal to 1/2 rho V2 squared minus 1/2 rho V1 squared. Okay, so this is where we sort of ended one of our previous applications of the Bernoulli equation. But now that we've sort of talked through our continuity equation application, we have one other equation that we can work with, right? We know that the mass flow rate at 1 is equal to the mass flow rate at 2. We can also express that as the density times A1 times V1 is equal to the density times A2 at V2. One of our key assumptions with an incompressible fluid, so densities cancel, and then we can put one of our velocities in terms of our other velocity. Right. Okay, so that's convenient because now we're essentially able to reduce unknowns. If we plug in this for V1 here, right, we can get our pressure drop in terms of only V2. Right, so we've essentially reduced an unknown. And in problems, you might be given information about V2, but not V1, and be expected to know that you can relate those two things by way of the continuity equation. Okay, so this from here on just becomes substitution, and you can work up an expression that looks like this. And simplify a little bit. So that's what this equation simplifies to. And what's that telling us? Well, it's telling us that in this application, right, we have A2 is bigger or smaller than A1? Smaller, right? So this term evaluates to a positive, right? Our velocity here is some number that is positive, but essentially just sort of looking at this equation, you can think through and see, similar to the conclusion we arrived at previously, that P1 is greater than P2. This right-hand side of the equation evaluates to be positive. We have that same scenario happening where we're increasing the velocity and the constriction, and we're doing so as a result of a pressure change, a pressure drop from P1 to P2. Right? So conceptually, we're trading these forms of energy. Mathematically, we see it play out. Yeah. Okay, so it's 10:01, so let's stop there and we'll pick up a few more examples on Monday. So homework thing will be posted this afternoon.